Hi guys, and welcome to video 14 in the But How Do It Know companion video series. And today we're going to be building our ALU. So in the previous video we saw how to construct an ALU using all the different functions that it's built from. And but what we're going to be considering as the ALU for our project today is going to be something a little bit wider in scope, and it's going to be all of this. So we still will have the ALU obviously at the center of this diagram right here, but we'll include in our ALU black box, if you want, the TMP register, the bus 1 circuitry, and finally the accumulator register, which is going to be included as well. So in totality, it's going to give us 8 input signals. So TMP set, bus 1, accumulator set, accumulator enable, and for the ALU directly, carry in signal, and 3 bits for the ALU up. We will also have 4 outputs, so carry out, A larger, equal, and 0 flags, which are going to be coming out of our ALU. So like I've mentioned before, and like we did with the RAM, we're going to be simulating the ALU using some software in the Arduino. So this is the code right here. Again, just let me remind you that this is not runnable code. I compacted it and took some shortcuts here to make it smaller and fit in the screen. If you want to see the actual code, just go to the GitHub repository. I'll put a link in the description box below. So we have on top our 2 registers, byte TMP and byte ACC, and the ALU loop, which is going to function a bit like this. So we start by reading what's on the bus and storing that in a temporary value. Then we check, is TMP set on? If so, take whatever was on the bus and store it in TMP. Then move along. Create another temporary storage called B and place whatever is in TMP in it. Then, if bus 1 is on, replace B with 1. The bus 1 circuit allows us to override whatever is in TMP temporarily to set it to the value 1. Then we're going to read the 3 signals that make up our ALU operation and create a number from those. We're also going to be reading from our carry-in pin, the carry-in value. We're going to be sending the operation code, A value, B value, and the carry-in to another function that's called soft ALU for software ALU. We'll see that one in the next image. So this function is going to do the computation for us of the different ALU functions and return 5 things, the actual result and the output flags of the ALU operation, namely C, A, E, and Z. And each of those are going to be sent to an output pin so that anything outside of our ALU circuit can read those. Then further down, if ACC is set, take the result, put it in ACC. And finally, if ACCE is set, so if we want to enable the accumulator, write whatever is in it to the bus. So moving on here to our second bit of code. This is just the soft ALU function. So basically what it does, it uses this switch operator here, which has one case for each of the different ALU operation codes. So 0 is add, 1 is shift right, 2 is shift left, 3 is not, 4 is AND, 5 is OR, and 6 is XOR. You also have 7, which is CMP, but the CMP does not really have an output value, so there's no need to consider it here. So depending on what the operation code is, performing the proper mathematical or logical operation and setting the proper variables, whether it be C the result or CO carry out. Then once that's done, we will set the other flags, namely a larger, equals, or 0, depending on the values of A, B, or C. And we will return all these values to our caller so that it can set the different pins, output pins, or the accumulator with those results. So what does that actually look like on our project board? It's going to look exactly like this. So the first thing we're going to do is add a new Arduino E1, and it's going to give us access to the extra pins that we're going to need to connect and interact with the ALU. So the first thing we do is going to be bring those two white wires from the main Arduino to Arduino E1, and that is going to allow the first one to access the pins on the second one and read or write the values that are required. So towards the bottom we have 7 of our 8 input signals that are there. So the first 3 on the left are the 3 bits of the ALU operation. And then on the right we will have the TMP set signal, ACC enable signal, ACC set signal, and bus 1 signal. So all of these input signals are going to go into the Arduino on different pins, which are going to be read by the code that we saw before. Then on top we will have to the right the carry in signal, and the reason why the carry in signal isn't sourced from the bottom of our project board like all the other inputs, it's because ultimately it's going to come from a different source, which we will see further along in the book. So for now I'm just setting it there. And to the left of that we will have output wires for our 4 flags, C, A, E, and Z, to which we're going to add some LEDs and resistors on top so that we can visualize what the values of the flags are. Don't worry too much about the preciseness of these LEDs and those resistors. Ultimately there's going to be some rework going up around there, but for now we just want to see what's happening inside through those LEDs. So that's it for now. I'm going to go and set this up, and then we'll take a look at it before looking at our test cases for the ALU, and then giving it a test run. So this is what the ALU looks like once it's set up on our project board. So we have our new Arduino here, E1. It's connected to Arduino main here with these 2 white wires. Then we have 7 of our 8 input signals coming up from down here, the 8th one being the carrying signal up here. And finally we have our 4 output flags, C, A, E, and Z, going to these LEDs and resistors on top. So in order to test this out, I've created a list of test cases, which is right here. So we're going to be doing at least one operation, one example, sorry, of each of the ALU operations to make sure everything is working properly. And we'll also be testing quickly at the end the bus 1 and the carry-in input as well. Before we do this though, I'm going to add a couple of things to the project board to make the testing easier, namely some push buttons and an 8-bit dip switch module. It's going to make it easier to enter the various ALU operations and set or enable the accumulator, which we're going to be doing very often in the test run. So I'm going to go off and do this. We'll look a bit at it and then we'll start with the test. Okay, so first what I did, I added some labels down here so that hopefully you'll be able to see a bit more which signal is which. Then I've hooked up this 8-bit dip switch module here to the three input bits for our ALU, so it's going to make it easier to select the ALU operation. I've also connected push buttons to the accumulator set and accumulator enable functions because we're going to be using those quite a lot. So when that's in place, we'll be ready to start our testing. It's going to be quite a tedious process because the reason for this is because this data input module that we have here doesn't really have an enabler to it. So if we want to set a value on the bus, we use the dip switches. Then we're going to ask the ALU to perform its computation. But when we want to view the results, we're going to press ACCE here. But first, we're going to have to put this value to 0 so that we only have one thing talking on the bus at once. So that means that for the next test, we're going to have to reprogram our data here. So it's going to be a lot of back and forth, but it should work nonetheless. So let's turn it on. So the first thing that we can notice here is that already we have two flags that turned on. So the equal flag and the 0 flag. And if you think about it, it makes perfect sense, right? Because we have nothing on our bus, 0 here, and the TMP register that is basically hidden inside our Arduino will be initialized with the value 0. So basically we're feeding two 0 values to our ALU, and it's telling us that the two values are equal. It's also telling us that the output is 0 because by having 0 selected here, which is in fact the add operation, 0 plus 0 equals 0, and that's why the 0 flag is selected here. So the first thing we're going to do is program the value 25 inside our TMP register. Okay, so I've set 25 here and I placed it on the bus. Now I will activate the TMP set signal to store it in there. So now our value of 25 should be stored inside of TMP. And a funny thing that's happening now is that the equal flag is still turned on here because we've set 25 on the bus, and when we've stored it into TMP, now effectively the A input of our ALU and B are both the same. But if I reset my bus here, then the equal flag disappeared. Now I'm going to set it to 12. So now we have 25 in TMP and 12 on the bus. So let's perform our first addition here. So operation code is 0. Let's set whatever value the ALU is computing inside the ACC. Now turn this off and enable the ACC to see our result. So we can see here the result is as expected in the table of 37. Now let's move on to the second operation, which is a shift right. So opcode is 1. Again, we will use our value 12 as a test value. So we have our input 12 on the bus, opcode set to 1. Let's store the result in the accumulator. Reset the bus. And check our result. Here our result is 6. So you can see that our value of 12 has been shifted right to the value 6, which comes out basically to dividing by 2. So now let's do the same thing with our shift left. Again, set our input to 12. store it inside the accumulator, reset our bus, and check the result. So now we can see that our 12 has become 24 as it's been shifted the other way around. So the next operation on our list is operation 3, the NOT operation. Right? So let's use our 12 again. Store the result of the NOT operation inside our accumulator. Reset our bus. And check our result. So now we can see that this effectively knotted our input. So for 12 we had these two LEDs on. Now they're all on except those two. So far so good. Our ALU seems to be working just as expected. So now let's move on to our logical operations AND, OR, and XOR. So AND is operation code 4. Set our bus to 12. So in this case, we're going to be ANDing 12 with 25, which is still inside our TMP register, and expecting a result of 8. So let's set the accumulator to capture the result. Reset the bus. And check our output. In fact, we're getting a value of 8. So our AND operation seems to be working properly. Let's move on to OR. Opcode 5. Set our bus like this. Store the result. Clear the bus. So and check our results. So now we're expecting OR of 12 and 25, which should give 29, and which is in fact correct. So 16 plus 8 plus 4 plus 1. So now let's check exclusive OR opcode 6. So we'll do our same test sequence here. Move our 12. Store the result in the accumulator. Reset our bus. Check the result. Result is now 21, just as we have in our table, and as we expect the result for XOR of 12 and 25. Now we're going to check the comparator. So the comparator is opcode 7. And set our bus as before. So in this case, the comparator is always actually on, just like described in John's book, so we don't need to fiddle around with the accumulator. Since it doesn't really produce an output, it's telling us that the output is effectively 0, so nothing is coming out of the ALU. We don't have a carry out in this case. Since we're comparing 12 and 25, A is not larger than B. And they are not equal. So our flags seem to be correct in this case. Now let's try something different and do a quick increment using the bus 1 signal. So let's go back to addition. So now the way we're set up with 12 on the bus and 25 in TMP, if we perform addition of these two values, we should get an answer of 37. But now we're going to use the bus 1 signal to overwrite the B value. So with this set up like that, we should be able to store the value inside of the accumulator. if we remove this, now if we check the result, we should have 13 because we used the bus 1 override. And that's the case. We can see that our bit is turning on. All right, so for the last test, we're going to test a bit the same scenario, but we're going to be activating the carry-in as well. So let's set our signal to 12. That's good. We're going to set our bus 1 as well. You see, as soon as we put the bus 1 signal, you can see the A larger flag lighting up, because when we use bus 1, B is equal to 1, but now our A is 12, so A is larger, and the flag comes on. I'm going to use another wire to set our carry-in. So everything seems good. Let's store it in the accumulator. Take this out and check the result. Clear our bus first, sorry. And our result is now 14. So our 12 plus bus 1 plus the carry-in. So everything seems to be working properly here. We've gone through all of our test cases from the table, and so far everything looks good. So one of the reasons that this testing was tedious, it's because we have to use our data entry module every time we want to set something on the bus. And the reason for that is because we do not have any registers. So that's what we're going to be doing in the next video. We're going to be adding registers to our project to make moving data back and forth between the different components easier. I'll see you soon.